Hi, everyone. Welcome to the Power Hungry Podcast. I'm Robert Bryce. On this podcast, we talk about energy, power, innovation, and politics. And we're going to talk about a lot of those on this podcast with Zabrina Johal. She is the Senior Director of Strategic Development at General Atomics and a recent acquaintance of mine. Zabrina, welcome to the Power Hungry Podcast.
Hi, thank you. Glad to be here.
Now, I didn't warn you. I warned some guests and other guests I don't. Guests on this podcast introduce themselves. So imagine you've arrived somewhere, you don't know anyone, and you have about 60 seconds to introduce yourself. Please tell us who you are.
60 seconds. Okay.
I'm not timing it, by the way. So I've
Okay.
it 62 seconds.
Give or take. So I started my career as a U.S. naval officer. I joined the Navy as a nuclear engineering specialist. And with that, had the opportunity to go to two different wars, deployed to the Persian Gulf. One was working on Tomahawk strike missile and guided missile destroyer driving the ship. And then the second one was on an aircraft carrier operating the nuclear reactor. I would say that experience really brought me out of the situation where I had grown up, which was Montana. There wasn't a lot of exposure, I would say, to the geopolitical stage and the defense arena. And I learned three big things that I think have driven me now through my professional career. One is the importance of nuclear technology to our national security. The second one is that we live in the best nation in the world. And I am a huge patriot for our country. And then the third one is the extreme sacrifice that our military service members and their family make every single day, and the importance of that to the United States and our national security. When I left the Navy, I joined a company called General Atomics. It's in Southern California. I've been there now for 17 years. So I have done a lot of different types of things, but we're really looking at innovation and those technologies that can change the world for the better. I spent a long time working on the fission side and, really on that intersection of technology to business and how you would commercialize. We started on the small modular reactor side and worked through that for a good decade. And more recently, I've been working on the fusion side, which is really interesting and a lot of developments in that area. Yeah.
Okay. That's somewhat more than 60 seconds, but we'll let you go. No, that's great. Well, I want to talk about all of those things. I think your experience in being in the Navy is interesting, especially operating a reactor. So, one question I'm dying to ask, since you just mentioned that. So, if the President of the United States went on board a Navy ship, could he get into the reactor room?
Oh, I was never in that situation, so I can't tell you. I assume yes. But there are many people who always want to go tour the reactor room. And of course, there are not many people who can. I think the president may get a pass for that.
Well, I assume the president, because he's the president, could say, well, that's what I want to do. But I don't know. I've just heard this rumor that he's not qualified or something. There's only a very select few people that can go into the reactor room. But let's talk about fusion first, because that was when we met a couple years ago. I knew you've been working on fusion, and I've talked to I talked to Ray Rothrock. He's been on the podcast. We talked about fusion some, but you have a front row seat, and General Atomics has been working on fusion now for decades. So the first question is, how important was this December announcement from Lawrence Livermore National Lab about that they had achieved a breakthrough where slightly more energy out than energy in? How important was that?
So there's a lot of backstory to this, and I don't want to get into detail. So to answer your question as put, it was significant because it basically showed that the physics behind more energy out than in is possible. A lot of people have equated it to the Wright brothers moment where they realized the physics of flight were possible, and now it's up to engineering and design and all these other things to actually make it economical. If we continue to talk a little bit about that experiment, that facility, the National Ignition Facility, is not a fusion energy facility. It is operated and or it's owned by the National Nuclear Security Administration. It is a nuclear weapons facility.
Uh-huh.
So the laser itself is meant to simulate conditions that you would see inside a nuclear weapon. It was never intended to make energy,
Huh.
if that
Okay.
makes sense. So when people ask, but isn't there so much more energy that went in to the whole system versus just the energy that went into the plasma and then the energy that came out? That facility was never, ever intended to actually do that. But the fact that it showed the physics were possible, that you could get certain phenomena inside that would actually cause this alpha heating and this gain, that was significant.
So it was 2 megajoules in. I remember reading about. Well, I actually did a short video on 2 megajoules of energy and 3 megajoules out. But I'm reading. This is a piece that just came out from J.P. Morgan. But read this. What it says here. Because I was familiar with these numbers as well. But it took 300 megajoules of energy to power the lasers, which produce the energy inputs, and even more energy to power cooling systems and computers. Also, the experiment was fired once at a single target and can only be done once per day. It required equipment housed in a building the size of a football field, and it generated enough energy to boil a tea kettle or run a hairdryer for 15 minutes. And then goes on and talks about it. And the bottom line with this assessment was, it's interesting, but the prospects not in my lifetime. So I've heard about fusion. I'm older than you are, but I've heard about fusion since I was a kid. I mean, does this really bring us any closer? Is fusion still 20 years away?
So I would say fusion is more like 10 to 15 years away.
Uh-huh.
And
And by what do you mean by 10 to 15 years away for what? I mean, for let's talk about commercial production of power. Was that 10 or 15 years, or you think it's further out than that?
so I would say a fusion pilot plant, right, which actually generates electrons from fusion energy is 10 to 15 years away. And then
Uh-huh.
just like on the fission side, you would have a FOEC, a first of a kind plant. And then you would eventually get to scale with an nth of a kind plant, driving down costs to be able to make electrons cost competitively.
So that pilot project, you're saying a fusion pilot project in 10 to 15 years, but then what about, I mean, this is the Holy Grail, right? We've heard that Wright brothers moment, the Holy Grail. But it seems to me that Wright brothers task was easier than fusion. I mean, okay, we get a pilot plant, let's say in 15 years. So let's say that's, we'll call it 2040. Then how long after that to be producing juice on the grid?
So then you would have to actually build and construct a plant that was meant for electricity generation.
Right.
So you could, call that five. And by the way, there are many other players in this field right now
Sure.
that have more, I would say, aggressive goals, targets. So there are, and there might be a little bit of a history lesson required here, but there are folks that are just now getting in with private fusion venture capital, venture funding.
Right.
And these folks obviously want to see something happen very, very quickly. If you were to look at, just to walk through, if you don't mind for a minute, the history of fusion to understand,
Sure.
because everyone's always said it's 20 years away.
Yeah.
And I think it's helpful to understand why this genealogy has happened. So it was in 1920s when a British astronomer looked at the sun and actually thought that it operated through fusion energy. Otherwise, it would have burnt out. And we knew within a decade later that he was right. The sun and other stars in our universe actually use fusion energy. So this is a combination of the lightest element that we know, known to man in the periodic table, hydrogen, fuses together to create energy. But the sun does it using gravitational fields. And so for many decades, General Atomics started getting into fusion energy in the late 1950s. People were trying to figure out this really, really hard physical phenomena because we don't have the gravitational fields that you would have up in the stars. And so it wasn't until the mid 1980s that General Secretary Gorbachev approached President Reagan and offered to pool all of the world resources, the people, the money, into a project, a big scientific project to actually prove feasibility of fusion. And that went forward. So that is ITER, which is now being constructed in the southern part of France with 35 different nations, as 7 partners, but because the EU is one of those, it's 35 nations.
Right.
And now you have
And
all of
just
these
to interrupt,
countries.
ITER is ITER, International. Well, I don't know what the acronym is here. I'm sure I could look
It
it up.
used to have an acronym, but now it just goes by ITER, means the way in Latin.
Right. Okay. Got it.
So very, very large, arguably one of the largest, if not the largest scientific collaboration in history in the world. And we're now almost 100% complete with construction and we'll start operation. But the whole point of it was to show that fusion is feasible. They obviously had to stop the design at some certain point in time in order to construct ITER. And so, there are many out there that'll say, well, ITER is an old design and it's not relevant, but that is not true. It's going to show that fusion is feasible. And then that is sort of like a demonstration facility, which from that point, it's up to each individual nation to develop their own roadmap to commercialize fusion. So we see the Chinese doing it very quickly, actually. We see the Russians, we see the Koreans, and now the United States has gone through a community planning process where they've actually laid out a roadmap. And there was a White House decadal vision that was put out last year looking at how to get fusion to the grid in 10 years.
Mm-hmm.
Right. So,
and if I can interrupt just real quickly on ITER. So this technology that's being developed there, assuming then all I don't know, like this is one of the reasons why I do this podcast. I get to learn about all these things I don't know about and ask questions that are maybe elementary for you. But is the technology then at ITER, then any country that's contributing can then use that same technology, that same engineering, that's going to be open source? Is that right?
That's right. So,
okay. So that's the benefit in theory of all these countries then coming together on this, was that they can then use that technology and bring it home and develop it in their own nation.
Exactly.
I got you. Okay.
The United States is paying 9% of construction costs, but we get 100% access to the intellectual property.
Gotcha. Okay.
And we also, for the funds that we're spending, that's coming back in country for technology development.
Gotcha.
So, for example, ITER, it's called a tokamak, which is a Russian acronym, but basically think of a donut-shaped device. It's a vacuum chamber inside the donut, and they put magnets around the outside and through the center, and then they put in isotopes of hydrogen, and they cause the hydrogen to fuse. General Atomics was commissioned many years ago. It's been 10 years now to build the central solenoid magnet, which is a magnet that goes down the center of ITER. Some people call it the heartbeat because it is a pulse magnet. It stands 49 feet tall. It can run 15 million amperes of current. When it pulses, it will provide enough force to lift an aircraft carrier out of the water. And so this is a superconducting magnet that General Atomics has made. It's the largest and most powerful superconducting magnet in history in the world.
15 million amps. So just I want to interrupt because your standard household plug will run at 5 amps, 10 amps maybe, right? A hairdryer would pull a couple or three. I'm testing my memory here, but no more than a single digit amps, right? We're talking about same with a refrigerator, right? And you just said 15 million. I just want to put that into scale. Amps, correct me if I'm wrong, if I've got my electrical terminology, this is equivalent to what you would call water pressure, right? That is the equivalence in electrical terms. Is that right? Or is it pressure or flow? I'm trying to remember. Volts. I get my volts and my amps mixed up.
Flow.
Okay, it's flow. So flow. Amperes are to water as if you convert electricity terms into water terms, it would be equivalent to water flow. Okay, so thank you.
Yeah.
And volts are pressure, and watts are gallons. That's how I think about, right? I mean, that's the common way to think about electricity in water terms. But anyway, I've interrupted now and for this diversion on 15 million amps. Which is an enormous amount of electricity flow.
Enormous amount of flow. And actually, I appreciate that analogy because when I was at nuclear power school, when they started teaching electricity, I just understood it so much better than I ever would by thinking of water.
Yeah, right.
Right? A diode and a check valve, all these things. Okay. So the way that this magnet will work is it gets stacked down the center of ITER like Legos. So they're circular, and there will be 6. And so we ship them independently. We We put them on a truck, we take them down to the port of Texas, put them on a barge, and send it over to ITER. So we've done that with 2 of them so far. The 3rd one is getting ready to go. And they're going to put these down the center of the tokamak of ITER. And it's enough force that the top 5 magnets physically separate from the bottom magnet when it's pulsed. So it is this amazing feature, right? But what it's done is it's allowed so much technology development in this cutting edge space to occur within General Atomics and the United States. So that's one example of what General Atomics is doing from a component provider perspective at ITER.
And these are superconducting magnets, so they're operating very low temperature then. Is that close to absolute zero? How close do they have to, how cold do they have to be?
4 Kelvin. And so these are low temperature superconducting magnets. There are others in the field that are looking at the high temperature superconducting magnet types. When the design for ITER was frozen, that was not as much in vogue. And there have been a lot of enabling technologies around magnet materials that are also part of the reason why, going back to your original question, why we think we're closer today to fusion. So when you look at certain enabling technologies that allow this extreme physics problem to become easier, materials technology is a big one, because you have to withstand, very high neutron radiation and absorption from the neutrons in a fusion system are more like 14 MeV, whereas the neutron in most of what we think of fission reactors, they're thermal, so they're around 1 MeV. And then a fast reactor gets up to 2 MeV.
Gotcha.
So
and just to back up, I'm sorry, just want to be clear on that. So the you said 4 degrees Kelvin. So this is 4 degrees above absolute zero. So this is minus 250 degrees F, something like that. Am I remembering my scale correctly?
Very, very cold.
Right. And so that's cooled then with liquid nitrogen. Is that the standard way to make that happen? Or is there another technology that you use on that? Or does that?
Yeah, that's the standard.
Okay. What I'm hearing you say, I'm interrupting a lot because that's what I do, but so General Atomics here is acting as a technology collaborator, as a manufacturer as well, right? So this is your how do you describe GA as a manufacturer, a technology company, all of the above? What is and tell me a little bit more about General Atomics as a entity. Where does it make its money?
So, and this is why I think I've stayed at General Atomics for so long, is it's all of the above. So we got our roots back in the 1950s, basically spun out of the Manhattan Project in a way. It was Edward Teller that developed one of our first devices, which was the TRIGA, which you've probably heard about. And we started working in fission and fusion at that point in time. Within the fusion space, then we went through actual models of earlier devices, prototypes, that then led to the D3D National Fusion Facility, which is a Department of Energy owned General Atomics operated facility in San Diego, California. This is the largest operating magnetic fusion facility in the United States. It's been in operation since the mid-1980s, and it's really operated impeccably. And it's a very different model because General Atomics is a private company that's been operating this. I think some of the private tenants that we take into operations and maintenance have helped that. But so from that point, we've understood how to maintain a fusion system, how to operate a fusion system, and how to design a fusion system. We also understand what goes into being able to actually see what's happening inside the reactor. And those are the diagnostics, which are extremely important in an experimental environment. If you're trying to do experimental science and learn something that then would inform a future generation design or even a feedback loop into the system. So I would say the major areas that we are into right now within the fusion space is design of fusion reactors, component technology, which includes diagnostics and magnets, and then the theory and computational modeling that goes behind how you would go into design and all of the advances that we've seen in high performance computing. Within a fusion system, there are just massive amounts of data. It's a plasma inside a fusion system. So a plasma is basically the forced state of matter, or it's when you strip the electrons from a nucleus and now they are in separate states. And they're zinging and they're moving all over. And you're generating all this data, but you need to be able to understand the data, make sense of the data, and then put something in place that could actually provide a feedback or something that would make the reaction operate differently if you wanted it to. So this is all the control, modeling, control system simulation.
Gotcha. So if I can stop you there for a minute, but General Atomics, you said you're a manufacturer, component provider, and you provided some of the components that were used at Livermore, as I read. In fact, I think you tweeted something out about that, if I'm not mistaken, or it was on LinkedIn. But you also make drones, right? Is it the Reaper drone that GA makes? What are you making that actually flies? What do you make that in the aviation world?
So and I want to get back to your Livermore comment because there's
sure.
a pretty big distinction there. But
okay.
General Atomics as a corporation has over 15,000 employees and 8 million square feet of manufacturing and office space.
15,000. Wow, I didn't realize it was that big. Dang me.
And we are a private corporation, so we have an owner. He's a very big patriot for our country. And part of what we do is, as you've suggested, we make unmanned aerial systems. And so these are planes that fly, but there is a pilot, but the pilot is not on board the plane.
Right. Yeah.
The pilot is operating the plane from remote control in a place very far from where the actual battlefield may be,
sure.
Right? Keeping the operator safe. This was a product line that we started getting into and developing in the 90s. And then it was really the war on terror in the early 2000s, where we realized that we are not at these big nation state wars at that point in time, but we really needed to go root out a terrorist somewhere. And you wanted to have something that could stay on station for long periods of time and be cheap.
Right.
And that was really where, and as you hear about them in the news, they're called drones, where that technology got started. And General Atomics was a pioneer in that era, and it really changed the face of warfare. You hear a lot about drones in the news and controversy around drones,
right.
But it changed everything by being able to take the pilot out of the cockpit, put them somewhere safe, have long station times. And, now you'll see a lot of various entrants. So we do the Gray Eagle, we do the Predator, the Reaper, the MQ-9 Reaper. And we're constantly innovating in that space and trying to, and it's not just obviously the airframe, but it's all of the sensors that go on board. So we specialize in a lot of the sensor type and again, aggregating the data and computing the data and understanding the data.
Gotcha.
So we have a whole, and that product is very much vertically integrated because of the need for supply chain,
right,
and being able to have a reliable supply chain. So through that process, we've just had amazing additive manufacturing, advanced manufacturing 4.0 principles that really go into the efficiency and optimization of making the product.
4.0 principles. I'm familiar with 6. Is this in the neighborhood of 6 Sigma?
This is like manufacturing industry 4.0, looking at, all of the from a systems perspective, the temperature, the pressure, the humidity, everything that goes into manufacturing and aggregating it in a digital way to make sure that you understand exactly what you're making, taking paper copies off the floor, these types of things.
Gotcha. And so, do you make your own jet engines for your drones? Do you make your own reciprocating engines, or do you outsource those?
Those are mostly outsourced, but we have done that when we've had to.
Gotcha. Okay, so I'm glad to get the big picture on GA because it's an interesting company. I didn't know it was at 15,000 and it's privately held. That's a lot of workers for a privately held company. But back to the component then that GA provided for Livermore that was involved in this fusion experiment that got so much attention in December. What was that component?
Okay, so the United States used to test our nuclear weapons underground. before that, we tested them above ground,
Right.
but we signed a moratorium in the early 90s where we stopped physically testing our weapons. However, we still need to validate and verify and update the nuclear weapon stockpile. So in order to do that, the government set up a network of national labs and lasers and facilities. So Lawrence Livermore has a national ignition facility. There's a Z facility at Sandia. There's a laboratory for laser energetics out at Rochester. There's a DART facility at Los Alamos. What all of these facilities need is they need a target. They need something to actually shoot with the laser, or at the Z facility with pinch with the accelerator. General Atomics has been providing those targets, they called it, for inertial confinement fusion since the program's inception on a sole source basis. So here we have over 30 years of engagement between General Atomics making the target and all of the national labs and the NNSA working together in order to understand how our weapons are aging. And that's not an area that we talk about frequently. However, it is a very, very important national security aspect for the United States. So what this means is, when I say a target, right, there are many different types. There's indirect drive, there's direct drive. The specific component that we made for Lawrence Livermore for the National Ignition Facility was a target that had about 35 components, believe it or not.
Okay.
And at the very center is a hollow BB. So a 2 millimeter spherical object. We call it a capsule. And we drill a hole in this capsule with a laser, and then we attach a fill tube because we have to get the isotopes of hydrogen inside this little tiny hole.
Right.
So the end of the fill tube is anywhere from 2 to 5 micron.
Okay.
And the exit is anywhere from 5 to 10 micron, depending on the design. The human hair is 100 micron on average. So we have to attach this fill tube into the capsule. Then we put it inside all this other machinery, a whole ROM, a thermomechanical package. We put it all together. We have a team of about 35 up at Livermore that do final assembly and work with the lab to put it in the experiment.
And this BB you're talking about, I read that it has to be the exterior of it has to be super consistent, very, very finely ground or so. I mean, this is the ultimate in precision manufacturing. As I recall, am I remembering the details about this object, how smooth it has to be?
That's right. So, and I don't
know why I remember this, but I do. But these targets, as you're called, these are not, you don't go to Walmart and get these. These are very hard to make, and you can only use them once. I mean, this is one of the challenges, though, isn't it? In terms of the longer view for fusion is, you're going to have to make a lot of these, or you're going to. Let me ask the question this way: what are the biggest obstacles as you see them now to fusion? Is it the material science? Is it, getting those components that are able to withstand all that neutron flux, as you talked about, the temperature? What are the key hurdles as you sit there and explain all of the science behind this? What do you think are the biggest hurdles now?
So there are 2 different types of fusion, and each have very different challenges. So the first one, where we were talking about ITER, that's magnetic fusion.
Okay.
This one that I'm talking about now is for inertial confinement fusion. But when we start thinking of energy, it's generally called inertial fusion energy.
Okay.
So IFE.
Okay.
So within an inertial fusion energy plant, you are absolutely right. You would have to be able to make these targets for cents, not thousands of dollars. And you'd have to make them very quickly, because the whole idea is that you would get some sort of insertion system. Think of maybe a target inserter, or maybe you're shooting these things into a laser chamber, and you'd be hitting them with a laser, causing fusion, extracting energy. That energy would go into a steam cycle. So
But you'd have
that's
to
the
do this, but
premise
you'd have to do
behind
it, but you'd have to do it over and over and over again.
over and over and over and over and over.
So then it's a manufacturing. I mean, it ultimately comes back to the supply chain manufacturing capability for the super high precision manufacturing. Then is that what, am I hearing you correctly?
Well, I think that, and so from the event, right, where we achieved ignition, and there were a series of experiments leading up to that that showed some gain.
Right.
They didn't technically achieve ignition, but they had showed some gain. We are now seeing private inertial fusion energy companies interested in this. And so when they, we are talking with several of these because we have been the target provider for many years.
I see.
But you'd want to, and they're all looking at different types of designs for their systems. But you're right. You would need to be able to create a target that you would have a manufacturing process in place that would reduce, the economies of scale would absolutely have to be there. You'd have to have some sort of way of making these things quickly with high precision, hopefully not the type of precision needed on the NIF design, because keep in mind, again, that NIF design was specific to experiments that they're doing to validate and verify our nuclear weapon stockpile.
Gotcha.
Not create energy,
right,
per se.
So to interrupt again, because I think one of the things that's interesting is that the amount of money, and I've been tracking this. I don't know whether I lose track of what I've written about and what I've just talked about. But you have TAE, California company. They've raised over $1 billion. Commonwealth Fusion out of Boston. They've raised, memory serves, $2 or $3 billion. I mean, there's a lot of money going to diffusion these days, and more than I can recall in my lifetime. So there was a lot of excitement and a lot of investment in fusion, in startup fusion companies before this experiment was made public at Lawrence Livermore. So there is a lot of excitement, but and a lot of money chasing this idea. But I just want to make sure I'm hearing you right, that you're saying one of the key obstacles is this supply chain, is this manufacturing capability for these components that are going to have to be used in any kind of commercial deployment of fusion. Is that right?
So for the Livermore experiential fusion, TAE, Commonwealth, General Atomics point system design, that's all magnetic fusion.
Uh-huh.
So depending on who you talk to, there are certain people that think magnetic fusion may be closer to reality than inertial fusion.
Gotcha.
Some others may have a different view. From General Atomics perspective, the Department of Energy, so let me backtrack a little bit. I mentioned that there was a bold decadal vision that came out of the White House, and they were talking about achieving fusion energy in 10 years. That then promulgated a series of actions where the Department of Energy there is an open solicitation right now to build a fusion pilot plant. So the government's idea is that we've seen greater than $4 billion being put into magnetic fusion over this short period of time, right? Because of that, they now want to generate a public-private partnership where the Department of Energy will pay a certain percent of costs, and they expect private industry to pay a certain percent of costs to get to conceptual design of a fusion pilot plant. So that is an open procurement right now. General Atomics is leading a team, one of the bidders on that procurement. And that idea is very much in line with what we saw on the fission side, if you remember, right? You look at fission technology development from a global scale. Well, U.S. companies are competing with member states. So we're competing with the Russians because they've chosen a design. They're backed by their government. We're competing with the Chinese and the Koreans. Same with U.S. fusion. So the government within the United States decided to follow the same approach. So right now, they are really expecting private companies to put together teams to provide cost share to develop a fusion system.
Gotcha. And so if you were going to, but if I'm hearing you right, GA and in its bid, your bet is on magnetic, not inertial confinement.
So On the magnetic side, we are a systems designer and a major component provider. On the inertial side, we provide targets and target injection systems and diagnostics.
Right. But but in your bid, what you're doing, you're saying TAE and Commonwealth, they're magnetic fusion companies.
That's right.
And
That's
are you, is that your path as well? Or are you magnetic or inertial confinement?
So for our path for our team on the bid, we are magnetic.
Gotcha.
So we are doing the tokamak design, which is basically, it was a prototype for ITER.
Gotcha.
It's what our D3D National Fusion Facility is. It's what we've been working in decades and decades.
Right. So what's the ante for the companies that are bidding on this? How much money are you going to have to raise to make this, to get the DOE money? Is it hundreds of millions, billions of dollars? What's the price tag?
So we're doing it in chunks, right? So the first chunk's conceptual design, then it'll be final design, then you'll actually get to construction. There are some facilities required along the way. So it's, hundreds of millions initially up to billions right? Fusion is very much like fission. It's probably a $4 billion venture to get from concept to commercialization.
Gotcha. So let's back up then about it. Just I want to talk about is the correct pronunciation TRIGA or TRIGA, TRIGA? Understand training, research, isotope, General Atomics. These are reactors that General Atomics has pioneered. Am I pronouncing it right? And what are they're micro reactors that are used mostly by universities? Is that am I remembering my history right?
Yeah. So TRIGA.
TRIGA. Okay.
TRIGA is that. Yep. So that's how you say it. That was General Atomics' first product. So when I talked about Edward Teller,
yeah,
this is out. This is mid 1950s era during Atoms for Peace. After Eisenhower gave his big Atoms for Peace speech about taking nuclear technology and now using it for peaceful purposes, there were several Manhattan Project veterans, like 30 of them, that came to San Diego under Frederick de Hoffman to build and design a friendly nuclear system. Nuclear technology wasn't that old at that point in time.
Right. Yeah.
And so they went from concept to prototype in 3 years on the TRIGA. And they actually have 4 different ideas. One was a shipboard reactor. One was a power reactor. This specific reactor, they wanted to be able to train high school students. So it would never melt down. They'd be able to train students and then do isotopes as well. Edward Teller led that. They eventually brought it to the Second Geneva Convention in 1958, an actual prototype of this thing. But General Atomics went on to build 63 reactors in over 20 countries in the world. Many of them are still in operation, many, as you say, at universities to train students.
And did you, I seem to remember a headline that you had, you're deploying more of them, or you've got some. Oh no! Here it was you're doing fuel production with Framatome for the TRIGA reactors, and that was a fairly recent announcement, if I'm correct. What is? I've been very interested. I'm pro-nuclear. I've been pro-nuclear for a long time, but I see a lot of obstacles. And I was in Japan for 2 weeks last month, and got a front row seat in what's happening in Japan. It made me more sober about the prospects for nuclear, and one of the reasons for my increased sobriety is the fuel cycle. Tell me about the fuel cycle for the TRIGA reactor and how it's different from HALEU or the low enriched uranium that are used in commercial reactors.
So the project that you're talking about is a joint venture between General Atomics, and it's gone through different names. It was originally Circa, now Framatome, where we have a fabrication facility in France that makes TRIGA fuel for these reactors around the world. And they just went through an upgrade to their facility, I think about $14 million upgrade to the facility to bring them back online to continue to provide the fuel. This fuel is very different than power reactor fuel. So these reactors are, hundreds of kilowatts.
So less than a megawatt thermal?
Yes, very, very small.
And they're not producing power. They're only thermal reactors.
They are not producing power. And they have they're not uranium oxide fuel, they're uranium zirconium hydride fuel. So it's much different than what you would think of for nuclear waste from, fission reactors producing power around the world.
Gotcha. And then the other thing that I saw that was interesting in terms of the headlines with General Atomics was a contract. I believe it was with the DoD for thermo-nuclear propulsion. What is that? What is it? I like saying thermonuclear propulsion because it's just got some certain ring to it. What is that? How would that work? Do we have thermonuclear propulsion now? What is that?
So NTP, right? Nuclear thermal propulsion. So this was a contract that General Atomics originally won with DARPA, which is a DoD agency looking at next generation technologies. And the project specifically wanted to develop a system that could get to the cislunar space, so the space between Earth and the moon. And specifically for this design, it's basically using uranium or plutonium that's fissioning to create heat that heats up hydrogen that goes through a nozzle that can provide thrust for a system.
Okay.
And most recently, which I think is super interesting, NASA and DARPA teamed up to pool their resources and really come up with a joint program on the next phase of this. We don't know yet where that's going to go, but ultimately, I think if humans want to colonize other planets, we absolutely have to use nuclear power. And this is a really exciting project moving us toward that space.
And we have to use nuclear because you just can't get enough kerosene together to get a rocket that high up into space that would last to travel into the further reaches. Is that another way to say what you're saying here? Why we have to use nuclear?
Well, so when you think of fossil fuels and chemical energy,
right,
you think about the electron cloud that surrounds the nucleus, making bonds with other electron clouds, and you split those bonds and you create heat.
Right.
Nuclear power, whether it's fission, which is the heaviest element, or fusion, which is the lightest element in the periodic table, it comes from the neutrons and the protons inside the nucleus. It's a fundamentally different reaction than the chemical reaction of the electrons making bonds, and it's 1,000,000 times more power dense.
Right.
So you could have 1,000,000 times less fuel for the same output, put another way.
Gotcha.
And so if you want to design a system that's actually going to get far enough, quick enough, and sustain long enough, I believe it has to be nuclear.
Right. Because there's just not enough. The mass of the chemicals that would be needed is just going to be too big, right? That the rocket would have to be too big. Yeah. Well, I like the way you explain that. So let me turn this back to you because, we've met a couple times and you have an interesting history. You were a female officer in the Navy. This was about 2 decades ago, if I'm remembering my history, right?
It's been that long?
Well, I'm not trying to betray your age or anything here, but these, the numbers are the numbers. And I read, I believe it was that you were one of the first female officers to deploy on a warship out of Pearl Harbor. What was it like? I can't imagine it being a guy, right? I can't imagine a lot of things, but being one of the only females, I don't know how many other females would be on board the ship in a ship full of hardheads. I mean, it'd be one thing to be on land, but you're on a very confined space. What was that like?
So, I would say it was very, very challenging. So
I would imagine that I think that might be the understatement. I was just guessing here, but the understatement of this podcast thus far, 44 minutes in, very challenging. And what was the most challenging of the challenging?
So I would say that growing up in Montana, I grew up in a very much equal environment. It didn't matter if you were male or female. We were all sort of treated the same, believe it or not.
And where in Montana?
In Billings, Montana.
Okay, so you lived in town. You weren't in the ranching business, or your family wasn't in ag. You grew up in the city.
If you call it a city, it had about 100,000 people.
Okay, well,
our nearest neighbor was, but I was not on a farm or a ranch. That's correct.
Okay.
So You're right. That might have been different. I don't know what the gender inequalities or imbalance may be on a farm or ranch. But when I first joined the Navy and, went through officer commissioning, and at officer commissioning or OCS, they did shave my head, which they told me that they would not do. And then the next experience I really had was they were going to send me out to a ship in Pearl Harbor. But at this point in time, these ships, so they were all guided missile destroyers at that point that they were trying to integrate. So you have about 220 people, and, maybe 25 or 30 of those are officers, and the remaining crew are enlisted personnel. And so their idea was that they would send two of us newly commissioned officers to a ship. They wouldn't just send one, they sent two.
Right.
And the idea is that we would be the first women on board, and we would integrate the ship, and that, they would start sending more personnel later.
Right.
So
2 out of 200.
2 out of 220.
Okay.
And so we got there. There were two of us. By the time that we deployed, there were four. So we had 4 women in a 3-man stateroom, and we would basically just hot racket. And they did not change.
Hot racket, meaning you didn't have a bed of your own. You would sleep in, one of you would rotate in a bed with someone else.
That's right. Or you'd sleep on the floor. And they did not change the restroom facilities. So they didn't actually put in female restroom facilities. So instead they put a flip sign on the door. So if one of us were in there, right, then all 4 stalls and 4 toilets were taken up. So I would say that the integration process was not smooth, that there wasn't a lot of pre-planning before just putting us on board. And I think that then caused a whole cast of difficulties and challenges for everyone. I think a lot of people, so before we got there.
And how long were you deployed then? How long were you at sea then when this, because I'm going to use the words thrown in the deep end, right? Thrown in the deep end on board a ship for how many months?
So this was, if you remember, President Bush saying mission accomplished.
Right.
On Abe Lincoln. It was actually that tour. So it was a 1-year anniversary of 9/11. We were deployed to the Persian Gulf. I was a Tomahawk strike officer. I was there for 6.5 months because I left to go to my nuclear power training. The ship itself, I believe, remained out there for 9 to 10 months.
It's a long time to be away from home, a long time to be at sea, and then also just dealing with those politics. I mean, well, I'll ask directly: were you harassed, hazed? Was that? I mean, how welcome were you, or how unwelcome were you?
So before we got there, the crew went through sensitivity training, and I think that everybody, there were different reactions to it. Some folks were completely terrified to even talk to us or approach us. And I don't know what they learned at the sensitivity training, but some folks were just bitter that we were there because we were inconveniencing an already hard lifestyle. And then there were some, I would say, sort of the minority that wanted to be our ally and reach out and assist. So
and all 4 of you were officers as well?
That's right. So we were all
so then you have a power dynamic. Not only do you have the gender challenge, right, but you have a power dynamic in that your officers dealing with a lot of enlisted men who are, they're doing the grunt work. They may have some resentment toward officers in general, but officers
that's right.
and female officers would make that doubly so, or I don't know if it's double or triple or what this percentage rate would be, but significant in any case. I've also done a little homework on you. So now, and I think we talked about this when we ran into each other in Washington, D.C., I think last fall. You're getting a PhD from the University of San Diego in gender studies. You're maybe pretty well equipped for this, aren't you? Why are you pursuing a degree in gender studies? Why? I know you have experience with these issues around gender and power, but why now? You're a mom, I believe. You've got a full-time job, and you're getting a PhD in this field. Why?
That's funny because that's exactly what my husband said.
Dear, what are you doing, dear?
Um, so I think because after the Me Too movement, I suddenly felt like I could talk about some of these hard things that we deal with, the unconscious biasing, just the relations between different genders. Ever since I've been at General Atomics in the field of nuclear energy and the field of fusion, there are very few women.
Right.
There are very few women in certain areas of STEM. The engineering fields and physics are probably the lowest represented by women. And so I felt like I was finally supportive enough and that there would be a voice and allyship to listen to the possibility of changing the situation.
Mm-hmm.
I think that no matter what situation you're in, if there's a huge gender difference or race difference or ethnicity difference, whatever it is, it will never be the same as just having equal representation where everyone has a voice to bring to the table. And it's really, really important. And so, it's always been a passion. And now I just felt like I had the time and the space to be able to actually make a change, because I don't want to, it's sort of like ripping off an old wound. It's really hard to talk about some of these things.
To revisit the challenges that you had while in the Navy on board. Was it on board as well as on land that the challenges were there, or was it just more intense on board?
More intense on board because the working environment and the stress levels are so high.
Right.
But even in the civilian sector, I see the same types of things going. They're nicer. They're maybe, they're not as overt, but they're still happening. And so
right.
I felt like an obligation to go back and do something to help improve the situation.
Well, it's interesting because, there are very few female nuclear engineers. I've had Maria Korsnick has been on the podcast, right? And she's a nuclear engineer. And obviously she's the head of a Nuclear Energy Institute. And I'm guessing, a peer of yours, roughly, I'm just guessing the same age as not supposed to talk about women's ages, but she's a mom, working mom as well. So when I looked at the fact that you're getting your PhD in philosophy from the University of San Diego, what's the title of your dissertation, or are you there yet?
Well, so the degree is a doctorate in leadership, which I think is super fun and then I'm specializing gender studies. So what I would really like to write my dissertation on is, they started integrating women on submarines 7 or 8 years ago, maybe a little longer now. And I would love to be able to do a study around that, maybe go underway with a submarine. I don't care if it's published or anything like that, but be able to just sort of do a climate survey and understand how they're handling it. Because from my perspective, what I had to go to on a surface ship was probably, it may even be harder for them on a submarine. I don't know. I haven't talked with any of those women, but I just think that I would have enjoyed having someone reach out to me, some way of communicating. I felt like I was isolated when I was on board and on deployment. And so trying to look at some of those issues a little deeper.
So I'm going to read this back and I'm just challenging you here. So you haven't arrived at a dissertation thesis then, or dissertation title? I mean, you got to write a dissertation to get the PhD, no?
Yeah, you do. So I'm in year 2. I fully expect this to take the full 5 years.
Okay. And how old are your kids? I'm just curious.
I have twins. They're 8 and 8, and then a 6-year-old, and they are a handful. Every single one of them.
Right. And you have plenty of extra time to work on a dissertation. So this is naturally what you want to do. But the dissertation you're saying would be something around the politics, the conflict, the friction around women in the Navy, in the submarine force. Is that's the general area that you want to look at? Is that, am I reading you right or hearing you correctly?
That's correct.
Gotcha. And so in 5 years then, or 4 years from now, or 5 years, we'll have to call you Dr. Johal then. Is that, that is,
you won't have to.
Won't. So let's talk about the Navy. I'm interested in the Navy. One of the other guests I've had on the podcast is Greg Easterbrook, who wrote a very interesting book called The Blue Age about the U.S. Navy and the importance of the U.S. Navy. And you've had a front seat to this and talked about the dedication of the U.S. military and how important it is. But it wasn't until I read Easterbrook's book, which I thought was really remarkably good. I really liked it, and I raved about it when he came on the podcast. But he makes the argument, well, two fundamental arguments. I think that one, the U.S. Navy has been indispensable in the trend toward globalization, that eliminating piracy, making all of the world's oceans safe for navigation, that it allowed global commerce to thrive in a way that's never happened before. But he also makes the same point that the following point is that we're neglecting the Navy. We don't have enough ships. Our capability is declining. At the same time, China is being more assertive in the South China Sea, the 9-dash map, all these other things that are happening geopolitically, and that it's a mistake. I think I'd paraphrase his argument very succinctly. He's saying it's a mistake to neglect this. Now, I'm assuming you're former Navy, so you're going to be pro bigger Navy, but walk me through how you see the Navy now and what you think needs to happen, and why is it not getting the love maybe from Congress that Easterbrook and other people think that it needs? How do you see it?
Oh, wow, that's a really tough question. And I'll be honest, it's not one that I'm following in terms of what the Navy needs moving forward. So I'll just give you my perspective. The naval power in the United States is second to none, right? The reason why we control the seven seas is absolutely our submarine force. The ability to go undetected for long periods of time and patrol waters has really kept our adversaries at bay. And that all came from Hyman Rickover, right? Being able to develop this nuclear technology. And then the nuclear fleet, the way that they train our officers and enlisted personnel to maintain the safety and the culture required to operate these safely. And really, no other fleet has any capability like that. The second piece of it is how important our aircraft carriers are. So being, an aircraft carrier has 5,000 people and 60 to 70 different aircraft, and they're all nuclear powered. And what that allows us to do is go into foreign operating areas where we don't necessarily have to have a base. And, it's absolutely those submarines and the guided missile destroyers that go with the battle group of the aircraft carrier to keep them safe from our adversaries. But it's allowed the U.S., which is relatively geographically isolated, to go into any operating point within the world and exert influence and power. And so if there's an expert in the Navy that's saying that we need to do X, Y, or Z, I absolutely think that we should be listening, and that Congress, obviously should be listening, because that's part of our world dominance. I would say the U.S. Navy and the nuclear weapons arsenal are the two things that, and sometimes a lot of American citizens don't want to face that fact, but that's why we are where we are in the position on the global stage.
That those are the key to our political and geopolitical influence. That the Navy and our nuclear weapons. So about those, you mentioned the nuclear weapon, the nuclear ships, and it brought me back to one of the other questions that I'm interested in. How are the nuclear? And the Navy has the best record as a nuclear operator of any nuclear operator in the world. I think that's a lay down hand. That's clear. How are the nuclear reactors? Who builds the Navy's nuclear reactors?
So they're built. So I know I went through a reactor complex overhaul in Newport News, Virginia, and there are defense contractors that get in there and they do work. You hear about BWXT doing the fuel, and then there are large Bechtel types, BAE systems, these types of
so Babcock and BWX. So this is Babcock and Wilcox, right? They've been one of the main suppliers, right? Is that right?
Yeah, and CBB, right? So these are big defense contractor type corporations. Huntington Ingalls, which was a spinoff of Northrop Grumman, that have technology around how to build the ships. And I would say out of all of the information coming from Department of Defense in the classified space, our nuclear technology information is the most closely held and carefully guarded.
Well, so that was my next question. So, how are these reactors different from the civilian reactors? They run on plutonium. They run on a higher enriched form of uranium. Is that right? What can you tell me about the? You were the you were managed the reactors on what aircraft carrier did you were you deployed on?
The Carl Vinson,
The
CVN
Car-
70.
Aha. And so, is that a single reactor vessel, more than one reactor? What can you tell me about the reactors and how they're different from the reactors that are in the civilian fleet for nuclear power production?
So the reactors on board ships are smaller than the civilian fleet, and they have higher enriched uranium. You have space constraints on board. You also have reactor power and operating limits that you have to watch very closely. So the envelopes are the margins are a little higher. On board an aircraft carrier like the Carl Vinson, you'll have two reactors. And, it's really all about reliability and redundancy. If one system goes out, what happens to the other? So there are safeguards in place where you'd be able to work the machining rooms together if something were to happen. We run casualty drills all the time in the Navy. That's really all we do, even while at sea,
Right.
to make sure that if there's any sort of mishap, we know how to recover the plant. We know exactly what to do. And so, yeah, so I would say, the safety culture within the civilian fleet is very, very similar, very heavily regulated, as I know you follow with the NRC, the Nuclear
Sure.
Regulatory Commission.
But these are still light water reactors. Then they're the chemistry is the same as what you find in the civilian fleet. And what about the output? What is the thermal or electric output on these? On that, is there a standard design for the Navy reactors? Do they have one that is a standard? I know Rosatom, they've used their submarine reactors are being deployed in PVIC and their power ships. One of their power ships that's been deployed in Siberia. Is there a standard size reactor that the Navy uses?
Yeah, so they have different standard sizes, some like the size of an SMR, others a little bit bigger. The amazing thing with the reactor, for example, on board an aircraft carrier, is that everything that has to do with energy or power comes from the uranium fissioning in the core. So we talk about these cogen plants, right, where you have to generate electricity, but then you also use a process heat or process steam type thing. On board an aircraft carrier, the uranium fissions, and then it goes into a secondary heat exchanger system, and that steam, does everything. So we pull up seawater and we distill it into drinking water. It goes through the ship's service turbine generator.
Right.
The older models of aircraft carriers would use the steam that goes into a catapult steam system to fire aircraft off the deck. Right. So it's just amazing the way that this whole system works and comes together.
And the new catapults, I think, are electric driven, right? Electric magnetic system of some kind. But you didn't tell me a rating number. Is there a reason for this? Or you're sworn to secrecy on the output of these reactors?
I'm not going to say a rating number.
Okay.
If you Google something, you Google something.
No.
I would say depending on an aircraft carrier or submarine, you'll get different types. Even within the submarine fleet, you'll get different types. But they're right around, an SMR or larger
Gotcha.
rating.
Gotcha.
But back to your electromagnetic aircraft launch system,
Yeah.
EMALS, that's a General Atomics product.
Oh, really? Oh, okay.
And that came from fusion.
Oh, really?
It came from a fusion scientist putting in a proposal to the Department of the Navy in the 90s, because we understand how to use magnets and systems for plasma. So they proposed it to be used on an aircraft carrier to fire aircraft.
And are they more powerful than the steam-driven catapults? I assume they're mechanically, well, I don't know about mechanically more simple, but you don't have steam, you don't have high pressure steam near in close to a bunch of working deckhands or whatever. Are they safer? They're more powerful? What is the difference?
So what they allow you to do is dial in the motive force more specific to the aircraft type. So we can now launch lighter aircraft and heavier aircraft. And we also don't put the same, the high stresses that you would put from a catapult system, which really only had a few ways of dialing in the motive force.
Oh, I see. With electricity, it's much more easily calibrated than with doing it with steam. I gotcha. And then that would be, Well, I don't know about the recovery rate, but yeah. Anyway, well, listen, we've been talking for more than an hour. My guest again is Zabrina Johal. She is the Senior Director of Strategic Development at General Atomics. You can learn more about her at ga.com and what General Atomics does. I didn't warn you about these questions either, Zabrina, but I always ask my guests two questions. First one is, what are you reading? I know you're doing you're getting a doctorate. You're a mom. You've got a job. You're fully employed. But you have books in your bookshelf on your nightstand? What are you reading in terms of when you have a few extra minutes?
So I actually read a couple books a week. That's how I regenerate. So when I'm not reading
a couple books a week, now you're leaving a lot of us in the shade here. Okay, well, you're overachieving again here, but what are they? What are the latest?
So I read a lot of leadership books, psychology of leadership, that I won't talk about those. I am reading The Future of Fusion Energy by Parisi Ball, which is a really good book that talks through fusion and brings it down to a level that I think most people would understand. I also, I just read Stephen King's new book, Fairy Tale.
A horror novel?
It's not horror.
Oh, okay.
Fantasy sci-fi, which is sort of my genre,
okay.
as well as psychological thrillers. I'm really into those right now. But A Ride of a Lifetime by Iger.
Okay.
Who actually was just brought back, right, to Disney. That's a fantastic book. It goes through all of the consolidation within the film industry.
Robert Iger, is that right? Am I right?
Yeah.
Oh, okay.
And then, I don't know, anything by Jared Diamond, Guns, Germs, and Steel, anything he's written a ton. You've probably read a lot of him, Jared Diamond.
Sure. Yeah.
Or Dark Sun, The Making of the Atomic Bomb by Richard Rhodes.
I've read some of Richard Rhodes. I need to. My wife Lauren loved his biography of John James Audubon. So that apparently is one of the best biographies ever done of Audubon. So Rhodes is he's very talented. So my last question, Zabrina, as I said, we've been talking more than an hour. You've seen a lot. You've been you've seen a lot of the world, and we've talked about some things that are sobering, some that are very interesting. What gives you hope?
Oh, what gives me hope? I think that, so, working in corporate environment, but then also having children, occasionally I get to go to their school and volunteer. And every time I go in, you just hear the laughter and you hear them running around. And I just think that the children are the future, and they're going to do great things as long as we're there to guide them. And I know there's been a lot of conversation around scaring children about climate. I think that's really, really sad that we should not be doing that, and instead talking about all the great things that they have in their future, teaching them about technology. So that gives me hope, thinking about them in 20 to 30 years.
Are you aiming your kids to be engineers like you?
I just want them to do what they want to do, where they're going to be happy and fulfilled. So,
yeah. Well, good. Well, we'll stop there. Again, excuse me, my guest has been Zabrina Johal. She's a Senior Director of Strategic Development at General Atomics. You can learn more about her and her company at ga.com. Zabrina, it's been great fun to talk to you. Thanks for your time, and thanks for coming on the podcast.
Thank you.
And thanks to all of you in podcast land. Tune in for the next episode of the Power Hungry Podcast. Until then, see ya.